Holy! Can you believe it? We are starting with the biggest topic that I've ever seen in my life. Alright, so what I want to do first is the following, right? I just want to mention that this is going to be a little bit of a longer video because I don't want to rush anything. I just want to take my time through this and I want to just go through certain examples, right? So the first thing we're going to do, we're going to introduce integration. What is the general formula for integration? How does it look after we integrate, right? Or how do we integrate? Second of all, I'm not doing definitive integrals. Definitive meaning like it's there. You have to calculate like areas under the function, right? Or under a graph. So we're not going to do that. I'm just going to be focusing on the general formula and how to do integration in general. There will be another video that will come out after this based on definitive integrals or definite integrals, however you want to say it. Okay. So let's just start with this right now. We have the following, right? So we are if you're new to integrals and you are watching my video, welcome. So what we are talking about over here is this is our integral sign. That is what we are introduced to in Calculus 2 or at the end of Calculus 1 when you're learning about antiderivatives. So integration is actually just antiderivatives. If you know derivatives, let's say for example you have a multiplied by x raised to the power of n, and if you want to find the derivative of that, right, so it's actually d by dx, this will just give you, it's going to be the exponent multiplied by the coefficient, like so. So maybe if I can write it like this, multiplied by the coefficient, and then multiplied by x to the power of n minus 1. And that is our power rule, right? So this is our power rule right there. So what I'm going to be doing, this is our antiderivative, right? So if I were to try and find the derivative of x squared, right? We know that the derivative using this method is just going to give us 2x, right? Because obviously we're going to take this power over here. We're going to multiply this power over here by the coefficient. And then we are going to minus this exponent by 1, which is just equal to 1, right? Which is represented right here. But we obviously don't write the 1 down. So when we are doing antiderivative, we're actually going to do the opposite. We're going to make it from 2x all the way to x squared. That is what I'm talking about. That is what integration in general is. If we were to talk about indefinite integrals and integrals in general. Definite integrals, there's a little bit more, actually not a little bit more, you know what I'm talking about if you've actually done it before. But yeah, let's not focus on this whole thing. This is just a little bit of a introduction. So now here is our formula, right? Here is our integral that we have over here, right? So we have the integral of nx raised to the power of m with respect to dx, meaning that dx is the variable inside of this integral. So if we do it with respect to dx, this means that the n and the m are both constants. Okay. You represent these as constants. Especially with derivatives. If I say d by dx of w, for example, right? Well, clearly, there's no x in here, right? So therefore, this will just be equal to 0, right? Because w is actually just a constant then. Because obviously it's not x. You're only taking the derivative properly if there's an x because of this, because it has respect to x. And if I say pi, by the way, I just want to clear things off. If the derivative of pi is it's not complicated. Pi is literally just an irrational number, 3.14159 to ... This is a constant, so that will also be equal to 0. I just want to establish that quickly. Okay, so let's get into the integration. So I explained that n and m are both constants where x is our variable which we are going to integrate with because it's with respect to dx. So let's move on to the formula. Alright, so this over here is what we have, right? So the integral of all of this is actually equal to all of this on the right hand side. Now let's compare it to the power rule, right? We can clearly see that when we're taking the derivative, right? So this is actually just our notation for derivative, and this is our notation for integrals, because obviously we can see over here. That's our notation for integrals. Now, what happened to our notation? So what do we note over here, right? Well, we have n x raised to the power of m plus 1. Now, what are we noticing over here, right? Remember that I told you that this is an antiderivative. And n minus 1 is what we would do when we're taking the derivative. But can you see that this exponent is now being added by 1 instead of minusing 1? Because now we're actually going to take the antiderivative, meaning instead of minusing 1, we're going to plus 1 instead. And I think the only different thing is that we are not multiplying this by the exponent, right? Because our general formula wouldn't work like that. It was determined by mathematicians that it wouldn't work like that. And then also for that to work, we also need to divide the whole expression here by, or the whole term here by m plus 1. Basically, this is exactly the same as the exponent. So let's use this. Also, I almost missed this, by the way. For some reason, students keep forgetting this. Plus c. Now, c, let's just take note of this, right? If you're taking the derivative of, let's say, for example, x plus 2, right? We know that the derivative of x is just equal to 1. And then the derivative of positive 2 is just going to be plus 0. Because the derivative of any constant is 0, right? Which will just give us 1. Now take note, if we were to take the antiderivative of 1, well, obviously with whatever we're having with respect to, we are going to include the variable, and I'll go into detail with that later. And we also have the constant. Don't forget about the constant, remember, because there is a potential constant that we may have taken the derivative of that just equal to 0. So that is why we say plus c. Plus c is some arbitrary constant. That is what plus c is, because we don't know exactly what that constant is. But when we do definitive integrals, we will likely be solving for c. But right now it's indefinite integrals, so we're not going to be focusing on that right now. So with that understanding in mind over here, let's move on to our first few examples. Okay, so like I said previously, this 2x would have given us x squared if we were to take the antiderivative. But let's just prove that that is the case, right? Let's prove that the integral of this is going to be equal to x squared. Plus c, because the reason why it's going to be plus c is because, remember, we don't really know if there was a constant initially. That's exactly why we put the plus c. We're uncertain about this, so we just added just in case. It could also, remember, constant could also be equal to 0, meaning that there was not originally a constant. So it could be any type of constant. Great. Now we're going to take the integral of this. How are we going to go about doing it? Now we're going to use the exact same rule that we used initially, which is going to be the antiderivative would have given us a multiplied by x raised to the power of m plus 1, all raised to the power of, all divided by m plus 1. Now let's use that, also plus c. Okay, so a value is clearly going to be 2, right? That's our coefficient. So which means we're going to do this, right? It's equal to the, so we're taking the antiderivative immediately, or we're integrating immediately with respect to dx. Okay, so we're going to have 2, which is the coefficient, multiplied by x, which is our variable that we're working with respect to dx. And then the exponent is actually just 1, can you see? So it's going to be 1 plus 1. That's our m value. All divided by 1 plus 1. Our denominator will always be the same as the exponent in this case. Obviously, if you do have a fraction, then that is a different case. But let's focus on this for now. And then plus c, because we don't know the constant. Now let's keep doing this. Let's just simplify further. 2x raised to the power of 2, because 1 plus 1 is 2, divided by 1 plus 1, which is 2. And what do we notice? Also, this is plus c. And what do we notice? these twos cancel, and then 1 is in the denominator, but then we can just write this as x squared plus c. Can you see that we have proven this? So that is how our antiderivative works. And someone came up with a formula that this will always work. Obviously, the plus c is an uncertainty, but it's absolutely fine. We are going to do a couple more examples here now. All right. So we have a polynomial over here, right? Polynomial function right here. A cubic function, to be precise. So let's look at, I'm going to actually go into more detail with our dx, right? So whenever you have these types of questions, right, when you have like a polynomial, let's take into consideration that this dx is only affecting all the terms that are on the left-hand side of it. Meaning if we have something like this, right, so if we have this whole integral like this, but then after the dx we have like plus, let's say for example, x. This means that it still only affects everything from the left-hand side of it, but it never affects this x. So which means this x will always stay the same when we are integrating. So just keep that in mind, please. That is, I'll do another example on this just to clarify. But right now, I want you to understand that the dx only affects everything. It's basically like trying to enclose, right? The brackets start where the integral, the right-hand side of the integral, and then it ends right before the dx. That's exactly what I'm trying to say. That is our notation. It's basically enclosed by these two things right here. So let's actually just do this, right? But this is actually an opportunity to teach you about something, some other rule that we have. So a rule that we have, if we take an integral of, let's say, x, so let's say ax to the power of n plus, and this is where this actually comes in handy, by the way. This is exactly what I'm trying to tell you about. If we have the integral of ax to the power of n plus, let's say bx to the power of m, right? If we have something like this, then, and it's also with respect to dx, what is this going to give us? So this will just be equal to, and we can actually write it like this. So obviously we have our brackets like that. We can actually take the integral into all of these terms because of the addition, and it also works with subtraction. But let's just work on this addition because that's our general way of doing it. This will actually be written as the integral of ax to the power of n with respect to dx plus, this is where our plus comes in, so it's basically this plus, and then it's basically going to be all of that with respect to dx. Both of them have to be with respect to dx, otherwise it won't work. So it's going to be that plus the integral of bx raised to the power of m with respect to dx. So that is what we can write it as. Note how this is how we linearize them, right, in terms of integration. So let's just do it, let's just use this method over here to answer this question over here. Alright, so we're going to say this is equal to, okay, so I obviously left this over here so that we can actually make reference to it, right? So I'm actually going to write my equals right here. So basically we can rewrite this like this. I know it's a lot of work that we're doing, but at the same time, it's just practice. This can be written as, because our brackets are like this, we're going to take the integral in to all of these terms that are affected between the dx and the integral. So it's going to be the integral of x cubed with respect to dx plus, because our signs are both plus, the integral of 2x squared with respect to dx plus the integral of 3 with respect to dx. And that is how we write it. Okay. Now, I know what you're thinking, by the way. You're probably going to be like, oh, then basically what we need to do is it's going to be plus c if we integrate here, plus c and then plus c. So therefore it will be plus 3c. Now, that's not how it works, by the way. How we actually supposed to do it is we have to integrate all of this and then we end with plus c only. Okay, so I'll show you what I mean. So we're just going to integrate all of this. The integral of x cubed with respect to dx is going to be, we can see the coefficient is 1, so that's just going to be x to the power of 3 plus 1 raised to the power of 3 plus 1 with respect, sorry, not with respect, it's going to be plus, we're going to have the integral of 2x squared with respect to dx, so that's going to be 2x to the power of 2 plus 1 raised to the, all divided by 2 plus 1, plus, and then we're going to have 3. Okay, here's the best part, by the way. We're going to have, whenever we have a constant, right, with respect to dx, this actually is affected. Because if we look at the following, right, if we look at the derivative, because I always have to make reference to the derivative because we're doing antiderivatives. If we look at the derivative of 3x, right, this will just give us 3 according to our power rule. And that's exactly what's going on here. We just need to, when we are integrating 3, we are going to get 3x instead. So it's basically the antiderivative. So this is going to be 3x. Okay. And there's no, we don't have to really use this because once again, it goes from a constant to a term, it goes from a constant towards in terms of x, basically. That's what I'm trying to say. And then we have to end off with plus c. And we can just simplify over here. X to the power of 3 plus 1 is just x to the power of 4 divided by 3 plus 1, which is going to be 4. Plus, and then we're going to have 2x to the power of 2 plus 1, which is 3, divided by 3, plus 3x plus c. And there's our answer. Let's do one more. Alright, so this is what I'm talking about here. Let's just, where are we going to integrate? That's the first thing we need to think about. It starts from this 3x squared and it ends right here. Remember, it's between the dx and the integral. And this plus 3 is outside of the integral, meaning that we're not going to be doing anything with it. Does that mean it's our constant? Does that mean that c is going to be equal to this? No, absolutely not. It's going to be 3, it's going to end with 3 plus c whenever we find the integral. Because once again, we don't know that constant. It's not going to be equal to 3. Okay. Cool. So this is what we're going to be doing now. Okay, I'm going to keep the bracket here actually, so that we know what we're dealing with. Now I'm going to say equals, and then obviously we're going to take the integral into both these terms over here. Therefore, it's going to look like this. It's going to be the integral of 3x squared with respect to dx. And then this is going to be plus because of our sign over here. And this is going to be the integral of x with respect to dx. And then this is going to be plus 3. 3, sorry. Can you see that we're not affecting 3 with any integral or dx, right? We don't have something like the integral with respect to dx. We just have plus 3. Okay. So that is what happens if we shift our dx. It only affects everything on the left-hand side of it until the integral symbol here. Okay. So this is going to be equal to, we're going to take the integral of 3x squared with respect to dx. That's going to be 3x to the power of 2 plus 1 divided by 2 plus 1, which is just, okay, and we're going to add the integral of x with respect to dx. It's just going to be equal to, it's going to be, our coefficient is 1, so it's going to be 1x raised to the power of, and our power is 1, so it's going to be 1 plus 1 divided by 1 plus 1. And this is plus 3 plus c. I always recommend putting plus c right at the end, because that is how we learn. I know, like I said before, there are students that forget the plus c. Fortunately, I'm not one of them. But yeah, it's fine. It's just a skill issue. 3x to the power of 3 divided by 3 plus, and then we're going to have x squared divided by 2 plus 3 plus c. And then we can actually simplify way further right now. And then this is going to be equal to, these will cancel. And then this will be, because this is 1 over here, it's going to be x cubed plus x squared over 2 plus 3 plus c. There we go. Beautiful question. Alright, so we're going to move on to something that is not a polynomial, but we are going to move on to rational integration with rational functions. Let's do it. So we have the integral of 4 over x to the power of 7 with respect to dx. Alright, so this is where we are going to do our stuff here, right? I know, okay, so this is what I actually should have shown you first, right? And this is an extra rule that we have, right? The integral of, let's say, ax to the power of n with respect to dx, for example, will be equal to we can actually just take the constant out. To make things easier, let's say that we're focusing on only when a is a constant. If a is a constant, then we can take it out. It's the same thing when we have limits, when we can take the constant out of the limit, and we can put it on the left-hand side of that limit. We can do the same thing with integration. So that is exactly what I'm trying to go at right now. Then this will just be equal to the integral, a multiplied by the integral of x to the raised to the power of n with respect to dx. Okay, so what I'm going to do is I'm going to continue the integral from here. We have the integral, we have a rational function. This is something new. So just as a test, obviously, you don't have to do this. You can go straight to the integration. But right now, I want to first focus on this. And I'm actually going to stress this more when we have something raised to the power of x to the power of 1. Right? Only when it's raised to the power, or only when it's divided by x. And it doesn't have any other degree. It's just 1. Let's just focus on this one quickly. We can also write this as the integral of 4 multiplied by 1 over x to the power of 7 with respect to dx, right? We can also take the 4 out, like that. And then because we have this constant like this, we can also write this as 4 multiplied by the antiderivative of 1 over x raised to the power of 7 with respect to dx. Okay. So because we have something like this, we can actually say that this is going to be 4. Now we're going to take the derivative. No. Before we take the derivative, we can also write 1 over x to the power of 7 as, so this is going to be 4 multiplied by the derivative, multiplied by the integral of, so this 1 goes over here. That's 1 multiplied by x to the power of negative 7. So we don't have to write the 1 here. So it's actually x to the power of negative 7 with respect to dx. Now we can integrate. We're going to say this is equal to 4. And remember what I said over here? This integral is only going to be affected with this one over here. We took the constant out, meaning it's going to look something like this, right? It's going to be 4 multiplied by the integral. That's exactly what's going on over here. And that's going to be, apologies, okay, the integral of x to the power of negative 7, we know the coefficient is 1. So that's just going to be, so we don't have to write that down. It's going to be x raised to the power of negative 7 plus 1, all divided by negative 7 plus 1. And with respect to dx, so that means it's just going to be plus c, like that. Okay. The plus c is outside. That's why I say always put it at the end. So then this is just going to be equal to, we're just going to say it's going to be 4. So the 4 is going to go into the numerator like this. It's going to be 4 multiplied by x to the power of negative 7 plus 1, which is just going to be equal to negative 6 divided by, and then this is going to be negative 6 over here. And this is going to be plus c. And then obviously we can simplify further. Then we can say that these will obviously cancel out over here. Oh no, these will simplify into, it's going to be 2 divided by 3. So then it's going to look like this. And then this is going to be 2 x to the power of negative 6 divided by, and this is going to be negative 3, like that. Okay. And also plus c, by the way. If you are not, if you can't keep it like a negative exponent like that, I do recommend simplifying it further. I'm pretty sure you know how to convert and then simplify. So I'm going to leave it at this point over here, and then for homework over there on your side, you can actually write this as a positive exponent by, and then see what you get as a final answer. Okay, you can let me know that in the comments down below. Let's move on to something brand new. Alright, so now we have the following question. Now you probably think that this is a pretty easy one compared to the last one, but let's just take a look at this quickly, and I'll show you why it's actually a little different. So here's a little bit of a trick over here. Whenever you have just a constant in the numerator, you can just take it over before the integral, like this. So it's going to be 5 multiplied by the integral of 1 over x with respect to dx. Okay, so if we want to integrate, okay, let's just first write this as a negative exponent. I'm just going to show you what happens. If you already know what the issue is over here, if you know what we need to do here. I don't recommend shouting behind the screen because I'm just trying to show you what happens if you just integrate further when x is only raised to the power of 1. So it's going to be x to the power of negative 1 with respect to dx. And this is just going to be equal to 5 multiplied by, and we know that the integral is affecting this entire thing over here, x to the power of negative 1. So this is going to be 5 multiplied by, 1 is the coefficient, so it's going to be x raised to the power of negative 1 plus 1 divided by negative 1 plus 1, and this is plus c. Okay, we simplify further, then we're going to have 5 multiplied by x to the power of negative 1 plus 1, which is 0, divided by negative 1 plus 1, which is 0. Ooh, here's the issue, you see. Now this is what I was talking about. We have something divided by 0, so you will immediately get an answer of undefined. But it's not actually undefined, right? What I want you to do is the following. Take into consideration, so we have to the power of 1 as the first degree polynomial in the denominator, right? So let's just take a look at this itself, right? So what do we know that's kind of similar to the antiderivative of 1 over x? If we take into consideration the derivative of ln x, right, we know that this is going to be equal to 1 over the inside of the bracket, which is x, multiplied by the derivative of x, which is just 1, so it's just going to be 1 over x. Doesn't this look kind of similar to what we're having over here? Well, yeah, of course, it's basically, but if we're taking the antiderivative, which we are saying over here, we're taking the antiderivative over here, like so, and then that's going to give us ln of x. Okay, now that we know that, let's get rid of all of this work that we've done. We know this is obviously going to be undefined, and that's not what we want. Because we know that the antiderivative of 1 over x will just be equal to ln of x. But is it just ln of x? I'm going to tell you why the integral of, I'm just going to quickly write it here rather. The integral of 1 over x with respect to dx is actually just going to be equal to ln of absolute value of x plus c. Why is it absolute value? Now, let's just take into consideration that if we have, the reason why it's absolute value is because absolute value of x will always be, always implies that it is, that x will be greater than 0, right? Or equal to 0. But in our case of ln of if we have ln of 0, that is undefined. So that's why our whole restriction will be where x is greater than 0, right? If x is negative in this absolute value, not in the absolute value, if x is negative in here, it'll be undefined. If it is equal to 0, it'll also be undefined. So that is why we have absolute value. It's the best we can do because basically it will convert immediately to a positive, right? Because we know that the absolute value of any negative number, like let's say negative 2, is just going to equal to positive 2. Because the absolute value, we can also write absolute value like this if it actually helps a little bit better. The absolute value can also be written as negative 2 squared like this, right? And then this will be equal to, and then we're going to have, but yeah, you understand what I'm saying over here, right? It's going to be positive either way because this square is going to affect this inside over here. And then, oh yeah, no, of course. This negative 2 squared is just going to be equal to positive 4. And can you see that this is actually equal to 2? I don't know why I was hesitating there. Positive 2. So that's exactly why we put the absolute value. Because we don't want it to be a negative. Otherwise, it's going to be undefined again. So let's just use that information to answer this question here. So this is going to be 5 multiplied by, and we should know already that the antiderivative of 1 over x with respect to dx is going to be ln of absolute value of x plus c. And then therefore our answer is going to be 5 ln of absolute value of x plus c. There's our answer. Can you see how easy this actually is? If we were to do the basically this rule over here, our general formula, we would get an undefined answer because it's divided by 0. Okay. So yeah, that is basically what happens when we have x to the power of 1 in the denominator. So that is kind of helpful, at least. Okay, here's our last one that I'm going to be doing for this video, for indefinite integrals. Now this looks weird, by the way. I'm just saying it off the bat. You're probably wondering, what is happening? Why is the dx on top over here? We have extra information here. Well, I mean, you should know what this is actually going to be. But let's just, and we also have a square root. Ooh, how intimidating, hey? I'm going to show you how we're going to break this down, right? So this is the integral of, and this dx, we know obviously that this dx is actually multiplied by 1, right? Which is actually the coefficient of dx. So we're going to take this dx to the bottom of the fraction, right? We can just take it out because it's in the numerator, so we can just take it out like that. So that means we'll just get 1 over root x with respect to dx. Just remember, it's still it is multiplying with dx, by the way. So I just want to let you know. But we always say with respect to dx because it's our notation. It's still multiplying by dx though. Obviously, there's just no way we can use algebra with dx unless we're doing integrals or if we're doing differentiation. Okay, so that's basically what it is. And then outside of this, we have 4x to the power of 2 plus 9. Now we can start taking the integral. But, whoa, we can't do that yet. Okay, first of all, we need to point out where we're integrating. We're integrating here, right? Only. Is there any other integrals? No, absolutely not. So which means we're going to take the integral. But first, before we take the integral, we need to change this square root to a power, raised to the power of a rational exponent, which is going to look like this. It's 1 divided by x raised to the power of a half. Can also write it like that with respect to dx. Oh, there we go. Making much better for ourselves. There we go. Now we can just take the derivative. So we have the, sorry, not the derivative. I keep saying derivative. It's the integral. Sorry. We're taking the integral of this now. Okay, with respect to dx. So it's going to look like this. Also, I just realized as well, it's actually going to be, it's going to be the integral of, it's going to be, so 1 is the coefficient, so it's going to be x raised to the power of negative a half. Remember, we must also write it like this. It mustn't be a rational function with respect to dx. There we go. So now we can actually take the integral. Okay, I promise we can take the integral now. So it's going to be like this, right? So we're going to write it into its form. It's going to be 1x raised to the power of negative a half plus 1 divided by negative a half plus 1. And this is plus 4x plus 9 plus c. Remember, we took the integral, and there we go. We have plus c at the end. And now we just need to simplify. We're going to have x raised to the power of negative a half plus 1, which is just positive half, divided by negative half plus positive half. It's just going to be 1 over 2. Plus 4x square, by the way. Sorry, I forgot about the square. Plus 9 plus c. Perfect. This is going to be equal to, we simplify. Now, obviously, we can write this as a, okay, so what do we note here? We can actually tip in times with this one, where it's actually going to be x multiplied by, where it's x divided by a half, we're going to actually multiply it by 2 instead. So it's going to actually be 2x raised to the power of a half. But remember, if you're raising something to the power of a half, it's actually going to be square root. So 2 multiplied by the square root of, square root plus, sorry, 4x squared plus 9 plus c. There's our final answer. So that is indefinite integrals.